Hello, everyone, and welcome to a webinar with FCI Aerospace, where we're going to be talking about thermal dispersion, which is a technology that they use in pretty much all their sensors. So you're in for a real treat. Before we get started, I just wanted to introduce my company. It's JD Technologies, and we're basically a field sales company that represents manufacturers. And FCI Aerospace is one of those manufacturers. We're serving the aerospace, the military and defense, the medical original equipment manufacturers, space, and industrial markets. And we offer a consultative style of selling, which is basically a more complicated selling where we're working closely with our customers and prospects and solving problems that they might have. We're not selling from a catalog. Everything we do is pretty much custom. And I did also want to mention that we are certified. Not everybody realizes that a rep firm can become certified. We're very familiar with ISO 9000 and the other certifications, but rep firms can also get certified. So we are an officially certified rep firm. Well, I wanted to introduce our speaker today, who's Dave Fiener, and he's New Business Development Manager at FCI Aerospace, which is now a brand of DwyerOmega. And I'm proud to say that we've been representing FCI Aerospace for over 10 years. So I've known Dave for over that period of time and then some. And he was the general manager when we met, running FCI Aerospace. He started with FCI focused on heavy industrial markets like petroleum, power, wastewater treatment, chemical food processing. We're going back decades, because FCI Aerospace, FCI, the company, has been in business since 1964. And after recognizing the significant benefits of thermal dispersion technology, Dave and his team brought that technology into aerospace. And we're talking about prime system customers that embrace this technology and using it on things like air management, fuel, liquid cooling, hydraulics, potable water, to name a few. And I can't list all the customers that they have because of the success that Dave and his team has had, but they include Lockheed Martin, Boeing, Northrop Grumman, and then on the commercial side, Bombardier, which is now Airbus, and Embraer. So it's an exciting technology, a lot of success, and we're looking forward to having this webinar. So without further ado, I'd like to introduce Dave Fiener.
Well, thank you, John, and thank you for all those that are attending. And as John indicated, although it is a webinar, feel free to put questions in so that John or I can respond to them at that time. And I'm going to keep the talk, hopefully, to the 45 minutes that we talked about. And as John said, we'll leave time in the end of the program so that you can raise any questions at that point too. I think John summarized FCI's entrance into the thermal dispersion market quite well, and we are one of the pioneer companies that use this technology as the primary method for detecting flow and liquid level. And there are a number of features of the thermal dispersion technology that make it particularly appropriate for aerospace applications. But before we get to those details, I'd like to just give you a quick overview. And it's probably particularly timely to have these shots that I'm going to present. So what is thermal dispersion? That's a pretty good question, but actually you Northeasterners probably know it well better than us that live in Southern California. And in fact, I think the winter storm Fern gave some practical experience. So as we begin, to yourself, just imagine who feels colder. Those that are in winter storm Fern with the cold temperatures but high wind blowing the snow around, versus the same temperature but no wind. So the primary difference between sensing the cold is the movement of the air over a heated body, which in this case is a person in the left-hand frame versus someone that is in a stationary air condition, as is the lady on the right-hand frame. So there's a significant difference in the thermal conductivity of the air moving over the heated body. So that's a primary example of thermal dispersion as a flow measurement. In regard to liquid level applications, we have an example of, on the left, you can see the polar bears are very comfortable in the air environment above the snow because air is a poor conductor of heat. And as a result, it doesn't conduct the heat away from the thermal body as much as these polar bears that are in the water. So one of the things we're aware of is that when people go into the water, they're subject to hypothermia at water temperatures that may not be that cold relative to a freezing temperature. And that's because of the good thermal conductivity of the water conducting heat off of the heated body, these polar bears on the right. So that's a good example of thermal dispersion with regard to liquid level. So how do we turn this into a practical measurement opportunity? And that is completed by FCI's founding fathers, Bob Dean and Mac McQueen. As John said, back in 1964, they developed a flow sensor that operates off of thermal dispersion, and it had a basic sensor element that looked like this. And you can see that the sensor head itself was a stainless steel probe assembly that would insert into a flow stream. And at the tip of the probe assembly were two thermal wells. In one case, there was a thermal well containing an RTD temperature sensor and a heater element, and we referred to that as the active or heated sensor. And then in the other instance, there is an RTD and reference sensor. And that sensor is the background temperature of the flowing media inside of the flow stream. So as a practical operation, we would heat one of the sensors to a temperature warmer than the background temperature and measure the background temperature with a reference sensor. So the difference in temperature between the heated sensor and the reference sensor became a good indication of flow, because as the flow stream increased in velocity or in mass flow, it would conduct heat away from the heated sensor to a higher degree than in a static or a no flow condition. And the initial products that we manufactured were flow switches. But as we developed the technology, we determined that the sensor element technology that we looked at, this delta T technology, worked equally well as a flow measurement device, as a flow metering device. So as we talk about the different products that came to be out of this technology of measuring differential temperature as a function of flow, we'll delve more into the different details of that technology. Now, one of the things I did want to mention, and that is that it took about 10 years, but we also determined that the same technology could apply to indicating the difference between a wet condition and a dry condition. And so we developed a product line of liquid level switches that also used the differential temperature technology. And those level switches, the delta T would be low when the sensor was wet, and the delta T would be higher when the sensor was dry, just based on the heat transfer capability of the media in contact with the sensor element. So as we worked with the sensors and the switches, we determined that there were some really, really compelling features. And as John indicated, initially they were applied to heavy industry, chemical plants, wastewater treatment plants, refineries. But we learned that similar problems of flow switch measurement occurred in aircraft applications as well. So what are some of the features of the sensor element that make it particularly compelling for these applications? Well, I have on the right-hand side, this is a flow switch which is commonly used on aircraft in air, in fuel, in hydraulic oil, and other media that you would find on an aircraft. And to clear how the sensor element looks, you can see that the tip is a stainless steel probe that has thermal well assemblies on the end. And in this case, it's a flange-mounted sensor that has an O-ring seal that enable it to go to very high pressures depending on the requirements of the application. The can on the back is hermetically sealed and contains the electronics that provide the heat to the heater element and measure the temperature difference between the active sensor and the reference sensor. And in addition, it has a circuit that provides an output. As a switch, the output is generally an open collector output that will either sync or open a circuit depending on the arrangement of that output, and sync either on flow and open on no flow, or open on flow and sync on no flow. So there's some variations that we can accomplish with the flow element itself. The other feature is that FCI has a extensive calibration facility, because this technology really depends on the ability to calibrate the sensor so that you have a very reliable, repeatable switch point. And here at FCI, we have the capability to flow virtually any media that would be used on an aircraft. That would include fuel, coolant materials like PAO, ethylene glycol. We can flow water, and of course we can flow air as well. So as we look at the sensor element, we start to see that there's some very compelling features, including a stainless steel all welded construction. So it's hermetically sealed so that any effect of the outside environment will not get to the electronics. It's compact and robust and a line replaceable unit. One comment to make with regard to that is these sensors often have mean time between failure calculations and practical field experience, which exceeds 100,000 hours MTBF. So they're very reliable devices. It's really tough to break one. And because they're solid state with no moving parts, they have a very long MTBF. So you can see the weight is low, in this case 0.45 pounds max. The flange mounted surface makes mounting it very easy, and it's possible with the settings of the screws that fasten it in place. You have an exact positioning of the sensor in the correct location in the line. As I mentioned, no moving parts, 100,000 to 200,000 mean time between failure. They're equipped with analog circuits. So in the aero industry that is concerned about firmware and software, there's no DO-178B required because it does not have any software on the sensor. The electronics are capable to 125 degrees C, and the probe or 250 degrees F, the probe to 175 degrees C or 300 F or more, depending on the particular requirement we're involved with. So tough applications like bleed air that go up to 500 or 600 degrees F, FCI has those thermal dispersion sensors operating in those applications. The switch point can be adjusted through the electrical connector for minor adjustments in the flow switch trip point. I already mentioned the different types of media that the sensor is used in on aircraft platforms, and the fact that we have the capability to calibrate in a wide range of fluids and piping arrangements at fluid components. And finally, FCI maintains qualified status on the units to all of the most recent qualification requirements. And in fact, we have a commercial off-the-shelf product line of these switches that have a pedigree of qualifications, which makes it quite easy to fit into numerous military and commercial applications. So here is a exploded view of the sensor assembly. You can see it's quite simple. Excuse me. Sensor element, mounting flange, electronics that are sealed inside of a hermetically sealed stainless steel can. We utilize a filter assembly to meet the EMI RFI requirements that are commonly encountered in the aircraft requirements as well. And you can see the configuration is quite compact and easy to apply in different applications. I did want to mention something. We'll talk more about it when we get into the flow meters or the flow transmitters. And so we'll move across to that. So I mentioned that flow technology was initially the product that we introduced, but soon we were able to transfer our knowledge into offering the flow sensors to meet flow meter applications, flow transmitter applications. And in this case, the electronics look at the delta T, but we changed the topology of the sensor element, not the topology, but the method of measuring delta T. And in the flow transmitters, rather than looking at the differential temperature between the heated sensor and the reference sensor, we use the same topology of a heater, two RTDs, but we control the current to the heater element so that we have constant power to the heater element, and the electronics, I'm sorry, let me change that. We have varying power to the heater element, and the electronics are held at a constant delta T and call for the electronics to vary the current to the heater element to maintain that constant delta T. So in that configuration, the measurement is actually the current to the heater. So in applications where we have we have no flow, we have a low current to the heater because it does not require much power to maintain the delta T at a particular no flow condition. But as flow increases, more and more power is required from the heater element to maintain the delta T. And that's an indication of a precise flow rate that's taking the heat away from the sensor element. So I have a couple, I have a slide coming up. We'll look at that in more detail. Again, the features of the flow transmitter, which make it desirable, include a stainless steel enclosure that is environmentally sealed, not hermetically sealed. So it has an O-ring and that makes this device repairable, whereas the flow switch generally is an LRU disposable unit. It has a 4-bolt mounting flange on the bottom, again, to hold the flow element precisely in the manner that the sensor was calibrated at FCI on the aircraft, so that there's no transfer error going from the FCI calibration facility to the aircraft. Typically, we have 3899 connectors or other MIL connectors that are used on military aircraft. In this case, the weight is more than the flow switch, but still quite low, 1.2 pounds max. Power input's 28 volts, aircraft power, so there's a range from 18 volts to 28 volts. Doesn't affect the accuracy of the device. The overall power consumption is less than 10 watts, even when it's at high flow and the heater is heating the active sensor to the highest degree it will. One of the really key features of the flow transmitter is the ability to provide dual output with flow as one output and temperature as the other output. Again, it's capable of wide temperature ranges from minus 40 degrees F or minus 40 degrees C to 350 degrees F, 175 degrees C. It can measure flow rates in liquid up to 10 feet a second and flow rates in gas up to 180 feet a second. The accuracy of the device is plus or minus 2% full scale, and the accuracy of the temperature measurement is plus or minus 2 degrees F. So it's reliable, used on multiple applications, commercial and military qualification pedigree, just like its little brother, the flow switch. And calibration and customers' media and piping configurations is available as well. So this flow sensor is used in many different types of applications. Liquid coolant for coolant, hydraulics, fuel, air measurement for cabin air, bleed air, many other different applications on aircraft. And here's the exploded view of this sensor element. You can see it's slightly larger, but it's still very compact. 5¼ inch from the top of the connector to the mounting flange for the electronics. And the flow element will vary depending on the installation. Generally, if we're in an application in larger ducting, we will extend the U length or the extension length of the probe to make the sensor mount in the center of the line. Output capability, in addition to having the 2 linear 0 to 5 volt outputs, some configurations also have switch outputs available. So open collector switch output is readily available too. Now I mentioned that the thermal dispersion technology is inherently temperature compensated, and let me talk a little bit about that. When we have a heated sensor and we have a reference sensor, as the background temperature changes, let's say your normal airflow temperature is cabin air at 70 degrees F, but in an emergency, the air temperature might go to 100 degrees F. So the reference sensor follows the background temperature of the process, while the heated sensor also follows the background temperature, and the delta T stays the same compared to the reference sensor. So just like in a differential pressure application where you're measuring background pressure and the pressure drop due to flow on the pressure sensor that is measuring the dynamic pressure. Similarly, we are compensated by using the reference temperature sensor to measure the background temperature. And under many applications, this works fine, but when you get very widely changing temperatures, there is a second order effect of the heat transfer capability of the air or the liquid changes as a function of that change in the makeup of the liquid as it's at a different temperature. Things like viscosity changes, specific heat changes. Those sorts of changes could result in an error on the thermal dispersion device if the sensor itself did not have a temperature compensation capability. And so here's an example of that kind of offset that you might find inside of an application without compensation. And you can see that this particular graph is an airflow transmitter with typical calibration curves in a 1.5-inch line. And in that line, as we change the air temperature, you can see that there is an offset in the reading at the same mass flow rate. And that error can add up if you're in a very widely changing temperature environment. So FCI's flow transmitters have a second order temperature compensation that will actually collapse these variations of the flow curve into a single output in spite of changes in temperature. And that is done through a series of calibration curves or calibration checks that we do at different temperatures. And we make an adjustment to the temperature compensation circuit. So we apply a slope and an offset to bring the curves together. So the result is, after we condition the signal output to be linear, you end up with a very accurate flow measurement in spite of changes in temperature across the flow range that you're interested in measuring. One other comment with regard to calibration, FCI has a sister company, Vortab company, which manufactures flow conditioners. And these flow conditioners are used when there are non-ideal pipe runs in the flow stream. And the flow conditioners are good at correcting errors that may result from a undeveloped flow at the sensor element, or a skewed flow profile at the sensor element, or swirl or rotation of the media at the sensor element. And so the Vortab flow conditioner is a product that can be used in conjunction with the FCI flow transmitter to improve the accuracy in very short runs of pipes, or in systems that may have other apparatus that are creating flow disturbances, such as pumps or two flow streams joining together. Those sorts of applications can be accommodated using the flow conditioner. One other thing we can do is we can actually configure the calibration stand to match the aircraft piping. And in doing so, we can calibrate as if the sensor element is on the aircraft and calibrate out, if you will, disturbances that are a result of the characteristics of the piping on the aircraft itself. So we have quite a bit of expertise developed from the flow conditioning experience, the flow measurement experience, and the operation of a world-class calibration flow facility for the last 40 years. So that's another feature that we can bring. So we mentioned the liquid level applications. You can see time-wise, we got another 15 minutes, so I'll go quickly through that. Liquid level uses the same technology in that we have a constant heater power and vary the delta T, and are able to indicate the difference between a wet and dry condition. But we have a second method of operation which has been used widely in gearbox applications. And this second application we refer to as the remote oil level sensor. And it's a simple single RTD sensor element, and we phase readings of that sensor element to determine if the sensor is wet or dry. And what I mean by phase, the sensor element is mounted in a condition, for example, a gearbox or other device that may have rapidly moving parts inside. And when an oil check is required to determine if the sensor element is above or below an oil level inside the settled gearbox, the system is unpowered and sets for a few minutes or a minute to allow the oil to go ahead and disperse back into the gearbox sump. And then the sensor element is pulsed with a low electrical current and the resistance of the sensor is measured at that moment. And that RTD is representative of a unheated RTD that's in the oil. Regardless of the temperature, it will give an indication of the background temperature of the oil. And then we apply an electrical current to that sensor element, which causes the element to self-heat. And as it self-heats, the temperature raises to a higher temperature based on the fact that it has an electrical current running through the sensor element. If that sensor element is below the liquid level and wet, it will have a small temperature rise because the liquid takes away the heat from the self-heated sensor. But if the sensor is dry above the level in the air or gas above the oil level, then the heat rise in the sensor will be much higher based on the fact the air or gas has a poor transfer of heat, and you end up with a higher temperature rise. So a customer's electronics, a FADAC or other type of device that they may have measuring electronics, can compare the two measurements of the start temperature and after 30 seconds the heat rise due to an electrical current, and can determine if the sensor's wet or dry. We kind of refer to it as an electronic dipstick because the sensor is very effective in indicating oil level in multiple applications throughout the aircraft industry. So single point level switches have the similar features, 28 volt power input, a output that sinks or sources to indicate wet or dry. In this case, the single point level switch can be mounted from the side, the top, the bottom, or even angled into the device or the system that it's measuring the level in. 100,000 plus hours of MTBF, no moving part reliability. We have external flange mounted configuration for reservoirs, sumps, and pipes. Wet, dry, or immiscible liquid interface. So what do I mean by immiscible liquid interface? This sensor, because the heat transfer between some liquid medias like water and oil are different, this sensor can be set to measure the difference between a water wet and an oil wet signal. So it can be used to indicate condensate in the bottom of a sump, or indicate in a collection sump whether or not it's water or oil that's being collected in the collection sump. And it also uses the thermal dispersion technology. For the single point remote oil level sensors I measured, they're very simple devices, as you can see. A single sensor like this can be internally mounted inside of a gearbox, and it's equipped with leads that can go outside of the gearbox to the customer's electronics that does the sensing, the determination as to whether or not the sensor's wet or dry based on the heat rise after a electronic current pulse to the sensor element. And as I mentioned, we refer to it as an electronic dipstick. which means that it's not required to send in a technician to look at a sight gauge that might be on the side of a hard to reach device like an APU engine or a electrical generator. So 200,000 hours proven reliability utilizing the FCI proprietary technology. So to summarize, as we draw to a close, the advantages of the thermal dispersion technology include the no moving parts reliability, rugged and high reliability, 100,000 plus hours MTBF, unaffected by contaminants because even if there is some debris that clings on the sensor element, if it's in the flow stream, it's still going to have the cooling effect of the flow over the probe. Or if it's in the level application, it's still going to have the change in heat transfer as a result of air to liquid. Virtually no pressure drop in flow streams, available in the flow transmitter with a temperature output, proven RTD type sensors, which are highly reliable and widely used in the industry. Low flow sensitivity, I mentioned, it's capable of measuring whispers of airflow or drips of liquid flow, and has been used in applications where it's trying to determine if a system is sealed and not leaking, particularly in aircraft refueling applications where you want to assure that the system is tight before you start loading it with fuel. One thing I didn't go into, we could spend the whole webinar talking about, is the advantages of mass flow measurement. The thermal dispersion technology, particularly in air applications, directly measures mass flow as opposed to velocity. And as a result of that, you don't have pressure and temperature devices as an alternate compensation that are often used in applications that are measuring velocity versus mass in flow measurement. Low weight and small size, and fully qualified across a wide range of requirements for both commercial and military requirements. And I should mention in closing, our applications are widely used in both rotorcraft and in aircraft applications. We have many, many installations on aircraft like the Apache, Sikorsky's product line. So we're very comfortable working in that environment as well. So at that, John, I'll go ahead and pass it back to you to see if there are any questions. Anybody would like any feedback on the thermal dispersion applications?
All right. Well, thank you very much, Dave. A really good overview of a not simple technology. You can really get into the details, but you gave a really good overview. So thank you very much for that. A couple of questions, and if anybody has any questions, feel free to either talk to me via chat or the Q&A. And if you want, we can turn on your mic. But while I'm waiting for additional questions, I did have a few that came in. One had to do with temperature sensing. And the question is temperature sensing strictly the RTD that's measuring the temperature and not related to the thermal dispersion technology, or does the TDT come into play, like for improving performance of measuring temperature, et cetera?
Okay. Well, thank you for that question. One thing, I did not spend a lot of time talking about how that thermal dispersion technology, the topology of the element itself. But if I understand the question is, how does the temperature measurement come into play? Well, as I mentioned, we have a heated sensor, heated RTD, and an unheated RTD. The unheated RTD directly measures temperature of the media, regardless of the flow rate. And that measurement is used to compensate in case the media temperature actually varies up or down, and it provides a reference to the heated RTD to determine what the delta T is,
Yeah.
as opposed to directly measuring the absolute temperature. But as I said, because we have this reference RTD, which is accurately measuring the background temperature in the sensor head, we often in the flow transmitter applications use it to replace a temperature sensor measurement that would be required if the customer, was
Okay.
trying to measure temperature too.
Okay. Good. That answers that one. Another one has to do with considerations for installing the thermal mass flow meter or transducer. How low of a temperature drop can you get? Do you start having issues if the pressure drop becomes too low?
Okay, so you said temperature drop and pressure drop. Let me
I'm
just say
sorry.
this.
No, I meant just pressure, just low pressure drop. The question has to do with low pressure drop. What are the key considerations when your pressure drop is low, not temperature? Sorry.
Okay, very good. So the technology for thermal dispersion is really not, does not depend on any pressure in order for it to operate. So
Okay.
it's not like a venturi or it's not like an orifice plate, which requires a pressure drop across the element in order for it to make its measurement. Now,
Mhm.
because you have a probe into the flow stream, there is a very nominal effect of the flow over the probe. So it's just trivial or almost unmeasurable amount of pressure drop that the flow element will create. And it, as far as the background pressure is concerned, the technology works equally well in low pressure or in high pressure applications. So from a functionality standpoint, we just need to know how it's going to be used so that we can do a calibration in the conditions that it'll be used on the aircraft. And it'll remain accurate even though you have changing pressure. And it
Mhm.
will create virtually no pressure drop at the measurement location.
Okay. Good. And finally, I think I know the answer to this, but I'll let you answer it. I might be wrong. But looking at the level switch and looking at it the way it differentiates in a liquid to liquid interface, like oil and water, how does it perform in if you have a liquid gas interface?
Well, that's the normal installation for liquid level is to measure the difference between a wet and dry.
Hmm.
In the industrial market, we've actually arranged them with two set points where one set point will measure, say, oil and water in a oil field separation vessel.
Hmm.
And then the other switch point will measure the difference between a wet condition and a dry condition so that they know that they do have liquid inside the vessel. And so the sensor technology will, again, it's dependent on the switch point setting, will indicate either liquid to liquid interface or it will indicate the difference between liquid to air interface. And then in some of those installations, I can remember I had one of my more memorable sales trips. I went to a Anheuser-Busch brewery, and they were trying to measure the difference between beer and foam on the beer inside of a storage tank. And so we retired to the break room and we were opening beers and pouring the beers into glasses and using the probe, and it successfully measured the difference between the beer and the foam on the beer. That was one of my more fun field trips that I made.
A tough job, but somebody has to do it.
Right.
All right. Well, I think that is it. So there are no more questions. Thank you very much, Dave. Thank you for everybody in the audience for attending. And as I said, you will be getting a copy of not only the webinar video, but a copy of Dave's presentation. And if you you want to take a deep dive into one of your applications, by all means, reach out to me and we'll set something up. So again, thank you very much and have a great rest of your day.